Welcome back. In this video, we're going to look at examples of finding area between two polar curves. Let's get to it. All right, so here's our first example. We want to find the area of the region inside r equals 2 and to the right of r equals secant theta. Okay, now the first thing that you should always do when you were told to find the area between two polar curves is to graph those polar curves. And so in this case, we need to graph r equals 2 and r equals secant theta. So let's start with r equals 2. Whenever you have r equal to some constant, the polar graph is just going to be a circle centered at the origin with a radius of whatever that value is that r is equal to. And here we have 2, so that means that the graph of r equals 2 will be a circle centered about the origin with a radius of 2. And I'm going to say that every 2 circles in this graph here is going to represent a unit of 1 for the radius. So the second circle here will be a radius of 1, and the fourth circle will be a radius of 2. All right, and so if this fourth circle is where we have a radius of 2, then the circle that represents r equals 2 will be this circle right here. All right, so that's r equals 2. Now how about r equals secant theta? Well, whenever you have r equal to some constant times secant theta, you are working with a vertical line. In this case, the constant being multiplied by secant theta is just 1. Right? We just have r equals secant theta. We don't have r equals 2 secant theta or 3 secant theta. And so since we have 1 times secant theta, that tells us that we are going to have a vertical line that crosses through the radius of 1 along the polar axis on the right side. If we had negative secant theta, then we would be on the left side. But since we have positive secant theta, we are going to be crossing through a radius of 1 on the right side of this vertical axis. So r equals secant theta will look like this. This is the vertical line that is represented by r equals secant theta. And so now we have graphed both of our polar equations, and we want to find the area of the region inside r equals 2, which would be inside the circle and to the right of r equals secant theta. So the area inside the circle, but to the right of this vertical line, is this area in here. So the area that we want to calculate is this region right here that lies between these two polar curves. And so how can we go about calculating this area? Well, since we have an area between two polar curves, we can use the following definite integral. The area is equal to 1/2 times the integral from alpha to beta, where alpha and beta are the two angles of theta that the region lies between. And we'll talk about that in just a little bit. But then inside the integral, we will have f of theta squared minus g of theta squared times d theta. All right, essentially what this definite integral is doing is it's calculating the area beneath one of the polar curves and then subtracting the area beneath the other polar curve. And so f of theta is the curve that borders the top of our area, or the top of our region, and g of theta represents the curve that is on the bottom of the region. Another way to think of it is that f of theta is your curve that has a bigger radius for the area that you want to calculate, and g of theta is the curve that has the smaller radius. Essentially what that means is that f of theta is the curve that is further away from the pole or further away from the origin, and g of theta is the curve that is the closest to the origin or the closest to the pole. And so if you look at our region here, this curve right here is the furthest away from the pole or from the origin. It has a bigger radius than this vertical line. And so this curve, which is part of the circle r equals 2, is f of theta. So r equals 2 is f of theta. That is the top curve of our region that we want to calculate the area of, which makes r equals secant theta g of theta. That is the bottom curve of this region because it is the closest to the pole. The radius of this vertical line is smaller than the radius of this circle for this region where we want to calculate the area. And so r equals secant theta will be g of theta. All right, so now we know what f of theta and g of theta are for this definite integral. Now the only thing that we're missing are the angles of theta, alpha, and beta. These are the two angles for which this region lies between. And so how do we determine what those angles of theta will be? Well, if you notice, this area that we want to calculate begins and ends at points of intersection between our two polar curves, right? So at this point right here and this point right here, our two curves intersect. So what we need to do is determine the angles of theta that correspond to those points where our curves intersect. And the way that we can determine that is to set our two polar curves equal to each other and solve for theta. And whatever angles of theta we get will most likely be the angles that our area lies between. So if we set these two polar equations equal to each other, we'll just replace r with 2. So we'll have 2 is equal to secant theta. I'll write that down. We have 2 equals secant theta. We just have to ask ourselves, for what angles of theta is secant equal to 2? Now, if you're not too familiar with the secant function, but you are familiar with cosine, then we can rewrite this equation to make it easier to solve for theta. Remember that secant theta is the same as 1 divided by cosine theta. So we'll have 2 is equal to 1 divided by cosine theta. And then what we can do is multiply both sides by cosine theta. So we'll have 2 times cosine theta is equal to 1, right? Cosine theta times 1 divided by cosine theta will just be 1. And then we have 2 times cosine theta. And then we can divide both sides by 2, and we'll have this. Cosine theta is equal to 1 divided by 2, or 1/2. Now, instead of asking ourselves what angles of theta for secant give us 2, we have a more familiar equation where we have cosine theta equal to 1/2, and so now we just have to determine what angles of theta make cosine equal to 1/2. And cosine is equal to 1/2 when theta is equal to pi divided by 3 and 5 pi divided by 3. At least for angles between 0 and 2 pi. We're only going to be looking at angles from 0 to 2 pi because in the polar coordinate system, one full circle is 2 pi. So if you look at angles beyond 2 pi, you're just going to have repeated points. You're going to be looking at the same points, but just where the angles are 2 pi bigger, which doesn't really change anything. So we only need to look at angles from 0 to 2 pi, which is what we have right here. Cosine of pi divided by 3, or cosine of 5 pi divided by 3, is equal to 1/2. So this angle right here will be pi divided by 3. So here's our angle of pi divided by 3. And then this angle right here will be 5 pi divided by 3. All right, so we will have 5 pi divided by 3. Okay, and so now we have determined the two angles that our region lies between. Now we just have to use those angles to help us set up our definite integral to calculate the area between these two polar curves. And so let's try that out. The area is going to be equal to 1/2 times the integral from some lower bound of theta to some upper bound of theta. Now, you might be tempted to make your bounds like this. You might write a lower bound of 5 pi divided by 3 and an upper bound of pi divided by 3, right? Because if you look at our area right here, it lies between this angle, 5 pi divided by 3, and this angle, pi divided by 3. However, it doesn't really make sense to integrate from a bigger angle to a smaller angle. It only really makes sense to integrate from a smaller angle to a bigger angle. So integrating from 5 pi divided by 3 to pi divided by 3 doesn't really make sense. And we also can't just flip these bounds of integration, right? We can't flip them in this way so that we have pi divided by 3 in the bottom and 5 pi divided by 3 on the top as the upper bound. Because if you look at the area between these two angles in this polar coordinate system, it's not this area. If we're looking at the area between pi divided by 3 and 5 pi divided by 3, we're starting at this angle right here at pi divided by 3, and we're going around this way to 5 pi divided by 3. From this angle to this angle, you're looking at a completely different area. We want this area right here between this angle and this angle. But we can't integrate from a bigger angle to a small angle, so what do? Well, what we have to do is represent 5 pi divided by 3 with a negative angle. All right, if this angle is positive pi divided by 3, and this angle right here is only one angle of pi divided by 3 less than 2 pi, right? If you add pi divided by 3 to 5 pi divided by 3, you would get 6 pi divided by 3, which is equal to 2 pi. So this angle right here could be represented as negative pi divided by 3. That would be the same thing as 5 pi divided by 3. All right, so in this direction, we have positive pi divided by 3, and then in this direction, we have negative pi divided by 3. And so if we use those two angles as our bounds of integration, if we make our lower bound negative pi divided by 3, and the upper bound positive pi divided by 3, now we are integrating from a smaller angle to a bigger angle, and the area between these two angles is the area that we want to calculate. We're starting at negative pi divided by 3, and we're integrating to positive pi divided by 3. Okay, so now we can fill in the rest of our integral here. f of theta is equal to 2, right? We determined that r equals 2 is f of theta. So we will have 2 squared minus g of theta squared, and g of theta we determined was secant theta. All right, so we will have secant theta squared and then times d theta. R equals 2 was the outside curve, and r equals secant theta was the inside curve. Okay, and so this definite integral that we have here can be used to calculate this area that lies between these two angles and is between these two polar curves. However, one more thing that we can do to make solving this integral easier is make use of symmetry. I always recommend that if you can recognize symmetry in the area that you want to calculate, that you make use of that symmetry to make your integration process easier. In this case, what we can do, instead of integrating from negative pi divided by 3 to positive pi divided by 3, which would work, this is an integral that you can solve to get the correct area, but what you could do instead is just calculate half of this area, because this is symmetric. We have the same area above the polar axis as we do below it. We can just calculate the area from an angle of 0 to pi divided by 3, which would calculate half of the area, and then just multiply that area by 2. All right, so what we can do is rewrite this integral. Instead of having our bounds of integration from negative pi divided by 3 to positive pi divided by 3, we'll have 1/2 times the integral from 0 to pi divided by 3. But then since that only accounts for half of the area, we then need to multiply our integral by 2. Okay? And so then the rest of the contents will remain the same. 2 squared is 4. So we'll have 4 minus secant theta squared, which will be secant squared theta. Okay? And so this definite integral, just like this one right here, also represents the area of this region. We're just calculating half of it and then multiplying it by 2 to account for all of the area. All right, and I did that because now it will be easier to calculate this area. We have a nice lower bound of 0 rather than negative pi divided by 3, which is a little bit ugly. Okay, but either way would work. You can leave it like this, or you can use symmetry like I did right here. And so now that we have this definite integral, let's work on solving it to find our area. All right, and so to simplify this, 2 times 1/2, that's just equal to 1. So 2 and 1/2 cancel each other out. And so we will have that this is equal to the integral from 0 to pi divided by 3 of 4 minus secant squared theta d theta. Now, integrating 4 and secant squared theta are actually pretty easy. We know that the integral of a constant is just equal to that constant times the variable of integration. So the integral of 4 will be 4 times theta. And then the integral of secant squared theta is also pretty simple. That's just one of our basic trig rules for integration. The integral of secant squared theta is tangent theta. So if we integrate 4 and secant squared theta, here's what that will be equal to. We will have 4 times theta minus tangent theta evaluated from 0 to pi divided by 3. So now we just have to evaluate 4 theta minus tangent theta at pi divided by 3 and subtract the evaluation at 0. However, notice that when we evaluate this at 0, both of these terms are just going to output 0, right? 4 times 0 is 0, and tangent of 0 is 0. So we're just going to be subtracting 0 when we subtract this expression evaluated at 0. So we really don't need to write that. We just have to evaluate it pi divided by 3. So this will be equal to 4 times pi divided by 3 minus tangent of pi divided by 3. And if you wanted to, you could write minus 0. But it's not really necessary because that doesn't affect our answer. All right, now tangent of pi divided by 3 is the square root of 3. And so this will give us our final answer that the area is equal to 4 pi divided by 3 minus the square root of 3. And so this right here is the area of this region that lies between these two polar curves. Okay, so that's it for this example. Let's take a look at one more example for this video. Okay, so here's our next and final example. We want to find the area of the region that is common to r equals -6 times cosine theta and r equals 2 minus 2 times cosine theta. Okay, so if we want to find the area of the region that is shared between these two polar equations, the first thing that we need to do is graph those polar equations. And so let's start with r equals -6 times cosine theta. Whenever you have r equal to some constant times cosine theta, you are working with a circle that is not centered at the origin. Specifically for cosine, you're working with a circle that you would find on the right side of the graph. And that circle would be split by the polar axis. However, Since our constant in front of cosine theta is negative, the circle is going to flip sides and reflect about the vertical axis. Instead of having a circle on this side of the vertical axis, it will be on this side. All right, and that circle is going to have a diameter of 6. And so if each of these concentric circles represents an increase in the radius by 2, then this first circle is a radius of 2, the next circle is a radius of 4, and then we have a radius of 6. So if this polar equation represents a circle with a diameter of 6 that is on the left side of the vertical axis and is split by the polar axis, then that circle will look something like this. Okay, so that takes care of this polar equation. Now how about this one? This polar equation is in the form of a limacon. The general form of a limacon is that r is equal to a plus or minus b times cosine theta. At least when you're working with cosine. This could also be sine theta, and you would still have a limacon. But we have cosine theta in our equation here. All right, now based on those values of a and b, which in this case are both 2, we can determine what type of limacon we are working with. And that is based on the value of a divided by b. In this case, since a is equal to 2 and b is equal to 2, that means that a divided by b is equal to 2 divided by 2, which is equal to 1. When a divided by b is equal to 1, that means that your polar equation represents a limacon that is a cardioid, or it's shaped like a heart. And so the general shape will look something like this. When you know you have a cardioid and you're working with cosine, your graph is going to look like this. You have this type of a heart shape that is symmetric about the polar axis. And this is how the cardioid is oriented, given that you have a plus b times cosine theta. But in this case, we have 2 minus 2 times cosine theta. So that means that our cardioid is going to be reflected about the vertical axis. So instead of looking like this, our cardioid will look like this instead. It will be oriented in the opposite direction. Okay, and so to quickly sketch the graph of this cardioid represented by our polar equation, and I'm going to graph it in this color, we need to identify some helpful points. And so a couple points to be aware of is that the back end is going to be at a radius of a plus b, and the cardioid will pass through the vertical axis above and below the polar axis at a value of a. And then, of course, this point is at the origin. All right, so a plus b is going to be equal to 2 plus 2, since a is 2 and b is 2, and 2 plus 2 is 4. So the back end of our cardioid is going to be at a radius of 4. And then a is equal to 2, so our cardioid is going to pass through the vertical axis at 2, this first circle, above the polar axis and below the polar axis. All right, so that's a radius of 2 right there, and that's a radius of 2 right there. So all we have to do to make our cardioid is start at 4, pass through that value of 2, meet at the origin, come back out, pass through 2 again, and come back to 4. So let's draw that. Here's what the cardioid will look like. It's not a perfect drawing, but it'll do. And now that we have drawn both the cardioid and the circle that are represented by these polar equations, we can see the region that we want to calculate the area of. We know that we want to find the area of the region that is common to both of these polar equations. So if you look at our graph here, the area that is common to this cardioid and the circle is the area that they share, this area right in here, the area inside the circle and inside the cardioid. And so if I shade that in, this is the area that we want to calculate. This is the area that is common to both the circle and the cardioid. And so the question is, how can we calculate this area? It's going to be a little bit different than our previous example, because when you're calculating the area of a region that is common to two polar curves, the process to calculate that area is going to be a little bit different than if that area was between the two curves. All right, and here's what I mean by that. This area on the outside here, this crescent-shaped area that we don't have shaded in, this would be area that is between the two curves, right? This area is between this circle and this cardioid. It is not a region that is common to both curves. It's outside of the cardioid, but inside the circle. But this region in here that we want to calculate, it is a region that is found within the circle and within the cardioid. And so the process for calculating that area will be different. But before we determine how to set up any definite integrals to calculate that area, what we should do first is determine the points of intersection for our polar curves. Where do they meet? Because that's going to be helpful in determining how we will actually set up our definite integral, or possibly multiple definite integrals. So what we need to do is set these two polar equations equal to each other and solve for theta. So if we do that in this case, we'll have -6 times cosine theta is equal to 2 minus 2 times cosine theta. By setting these two polar equations equal to each other, we can solve for theta, which will give us angles where these two polar equations intersect. In particular, we're looking for the angles of this point right here, and I'll mark these points. This point right here, where our two curves intersect, and this point right here, where our two curves intersect. We want to know the angles that correspond to those 2 points. That's going to help us determine where the area is located so that we know how to set up our definite integrals to calculate that area. So let's solve for theta here. First thing I'm going to do is add 2 cosine theta to both sides of the equation. -6 cosine theta plus 2 cosine theta will be -4 cosine theta, and that will be equal to +2. And then we can divide both sides by -4 to have cosine theta is equal to 2 divided by -4, which reduces to -1/2. So we'll have cosine theta is equal to -1/2. And so now we just have to ask ourselves, for what angles of theta is cosine equal to -1/2? And if you're familiar with cosine, you know that cosine is equal to -1/2 when theta is equal to 2 pi divided by 3 and 4 pi divided by 3. Those are the two angles of theta for which cosine is equal to -1/2. All right, and so what that tells us is that at the angle of 2 pi divided by 3, our two curves intersect, and at an angle of 4 pi divided by 3, our curves intersect again. And so an angle of 2 pi divided by 3, that's 2/3 of the way to pi, that corresponds to this point right here. So this angle right here is 2 pi divided by 3. And then 4 pi divided by 3, that's 1/3 of the way to 2 pi, right? 3 pi divided by 3 is pi, and so another pi divided by 3 will take us 1/3 of the way to 2 pi. So that corresponds to this angle right here with that point, and so that is 4 pi divided by 3. Okay, so now we know the angles of the points where our two curves intersect. And so now before we do anything, I want you to take a close look at this area and these angles. Because if you look really closely, you can see that all of the area that we want to calculate actually doesn't lie between both of those angles, right? We have a little bit of area here that is before this angle of 2 pi divided by 3. That's not an error on my part in my drawing. That is actually a little bit of area that occurs before that angle. And then down here, we also have a little sliver of area that occurs after an angle of 4 pi divided by 3. And so this is why calculating area of a region common to two polar curves is a whole lot trickier than just calculating the area between two polar curves. All right, we typically treat them as the same concept. We kind of lump them into this same topic, but really the process of calculating this area is going to be different. Because if we were calculating the area of this crescent shape that we don't have shaded in, this area would lie between this angle right here and this angle right here. Between those points of intersection, that's where that area lies, between those two curves. But the area inside the two curves doesn't just lie between those two angles. There's a little bit of area before and after. And so if we take a closer look at this, I'm going to graph each of those curves again, but in their own separate coordinate planes. Right here, I'm going to graph that circle. That looks a bit like this. And then over here, I'm going to draw that cardioid. So that looks a bit like this. And then if I add our lines for the angles to each of these diagrams, here's what that will look like. We'll have an angle of 2 pi divided by 3 right here, and an angle of 4 pi divided by 3 right there. All right, so that's 2 pi divided by 3 and 4 pi divided by 3. And then for this graph, I'll draw those same angles. Here's 2 pi divided by 3, and here's 4 pi divided by 3. All right, and now what we can do, the reason that I drew both of these polar graphs separately, is we can look at this area in a new way. We can break it up into pieces that are easier to see how to calculate the area of. And so what I want you to notice about this area is that it's inside the cardioid, but only up until the edge of the circle. Or I guess I should say this curve of the circle. That's how far up the area goes. All right, and so this little sliver right here and this sliver right here of area is between this angle of 2 pi divided by 3 and this angle of 4 pi divided by 3 and this curve of the circle. So that area would be right here and right here. All right, so I'll shade that in. These are the two slivers of area that rest outside of those two angles where our two curves intersect. And that means that the rest of this area is going to be in here, inside our cardioid. It's the area between the two angles that is also still inside the cardioid. It does not reach outside of it. So now you can see visually that together, these two slivers of area and this big chunk of area would make up the area of this region right here. All right, and so what we can do to calculate this area is calculate the area of each of these sections individually and add them together. Because the area of these slivers, it's just the area beneath the circle, right? It doesn't have anything to do with the cardioid. This little sliver right here is the area between this angle of pi divided by 2 and this angle of 2 pi divided by 3. And then, of course, this sliver of area would be between this angle of 4 pi divided by 3 and this angle of 3 pi divided by 2. And then in the same way, this area is just the area beneath this polar curve between these two angles of theta. And so we can just calculate the area of the slivers and this chunk separately with separate definite integrals. All right, but to make it easier for ourselves so that we only have to use 2 integrals and not 3, because we would have to use 1 for each of these two slivers because they occur between different angles, and then we would use a third integral for this area. What we can do instead to only use 2 is make use of symmetry, because both this cardioid and this circle are symmetric about the polar axis. And so what we can do is just calculate the area of one sliver and calculate the area of half of this chunk and then multiply that area by 2. That way we have less integrals to work with, and actually calculating that area should be a lot smoother. All right, so here's what we're going to do. We're going to set up 2 definite integrals to represent this area in here that is shared by these 2 curves. And we're going to be multiplying both of those integrals by 2. So I'm going to have 2 times the integrals that we write. The first integral that I'm going to write will represent the area of this one sliver. And we're going to be setting up that definite integral using our formula to calculate the area beneath a polar curve, which if you're not familiar with that, it's a equals 1/2 times the integral of r squared d theta. And of course, there are bounds of integration there, which would be alpha to beta, the 2 angles of theta that the area lies between. All right, so this is the form of a definite integral that we're using. So if we do that in this case, we will have 1/2 times the integral from pi divided by 2 to 2 pi divided by 3. So we'll have pi divided by 2 to 2 pi divided by 3 of r squared, and this circle is represented by r equals -6 times cosine theta. So we'll have -6 times cosine theta squared times d theta. This right here represents the area of this little sliver, and we're multiplying it by 2, so that will calculate the area of both of those slivers, which is part of the area of this common region. Now let's set up an integral for half of this region, because we are multiplying it by 2. We are going to be integrating from 2 pi divided by 3 to pi, right? This angle right here is pi. So we'll have plus 1/2. Remember, we're adding this area, not subtracting. And then we'll have the integral from 2 pi divided by 3 to pi of r squared. In this case, this cardioid is represented by 2 minus 2 times cosine theta. So we will have 2 minus 2 times cosine theta squared times d theta. All right, and so this right here, these 2 definite integrals added together and multiplied by 2 will represent the area of this entire common region for these 2 polar curves. Okay, so now what we have to do is simplify these definite integrals and solve them in order to find the value of that area. And so let's work on that next. All right, so the first thing that we can do is notice that multiplying 2 by both of these definite integrals is going to cancel out with these 1/2. So this 2 and these 1/2, we don't need to write. They cancel each other out. So the area will be equal to the integral from pi divided by 2 to 2 pi divided by 3 of -6 times cosine theta squared. So now if we square -6, that will be 36. And then we can square cosine theta to get cosine squared theta. So we'll have 36 times cosine squared theta d theta. And then we'll add that to the integral from 2 pi divided by 3 to pi of 2 minus 2 times cosine theta squared. So now we have to square this quantity, which we can do pretty easily. There's a little trick that we can use. We just have to square the first term, and then add that to these two terms multiplied together, but then multiplied by 2, and then add that to the last term squared. So the first term squared, 2 squared is 4. So 4 plus 2 times negative 2 times cosine theta. So that will be negative 4 cosine theta. But then we need to multiply it by 2 again, which will give us negative 8 times cosine theta. So I'm going to erase that plus sign, because now we will have negative 8 times cosine theta. And then we'll add that to the last term squared, and we have negative 2 times cosine theta squared, which will be positive 4 times cosine squared theta. All right, and then don't forget d theta. All right, now if we want to integrate these two integrals, notice that we have cosine squared theta here and cosine squared theta there. In order to integrate cosine squared theta, we have to rewrite it using a trig identity. This is a technique that you learned earlier in Calculus 2 with solving trigonometric integrals. And so let's rewrite cosine squared theta in both of these locations using an identity. And so that will look like this. This will be equal to the integral from pi divided by 2 to 2 pi divided by 3 of 36 times cosine squared theta, but we're going to rewrite it like this. We'll have 1/2 times 1 plus cosine of 2 theta d theta. And we'll do the same thing for this cosine squared theta as well. Okay, so we'll have plus the integral from 2 pi divided by 3 to pi of 4 minus 8 times cosine theta plus 4 times 1/2 times 1 plus cosine of 2 theta. And then there should be a d theta there, but I ran out of space. We'll take care of that with our next line of work. Okay, so to simplify, 36 times 1/2 is 18, and then we can pull that 18 out to the front. So this will be equal to 18 times the integral from pi divided by 2 to 2 pi divided by 3 of 1 plus cosine of 2 theta d theta. And then we'll add that to the integral from 2 pi divided by 3 to pi of 4 minus 8 times cosine theta. And then we have 4 times 1/2, that's equal to 2. And then I'm going to multiply that 2 through this quantity. So we'll have 2 times 1, which is 2, and 2 times cosine of 2 theta. And so we'll have plus 2 times cosine of 2 theta d theta. Okay, and so now what we want to do is split up these integrals into several integrals. We'll have an integral for 1 and an integral for cosine of 2 theta, and then we'll have an integral for each of the terms in this integral as well. But before we do that, just note that 4 and 2 can be combined to be 6. They're both constants. And so I'm going to do that right away, actually. I'm just going to rewrite this. We'll have 6 minus 8 times cosine theta. That way we can go right from this step to the next step, which is to split this up into 3 integrals for each term. Now the reason we're doing that is because cosine of 2 theta in both cases is going to require the use of u substitution, so I kind of want to separate that from the other terms when we integrate. So we'll have that this is equal to 18 times the integral from pi divided by 2 to 2 pi divided by 3 of 1 d theta plus 18 times the integral from pi divided by 2 to 2 pi divided by 3 of cosine of 2 theta d theta plus the integral from 2 pi divided by 3 to pi of 6 d theta minus, because we have negative 8 cosine theta, the integral from 2 pi divided by 3 to pi of 8 cosine theta d theta. And then finally we have plus the integral from 2 pi divided by 3 to pi of 2 cosine of 2 theta d theta. Okay, and so now we have split up these two integrals into many different integrals. And so now what we can do is work on integrating. This integral will be fairly easy to integrate as well as this one and this one, but these two integrals where we have cosine of 2 theta, those are going to require u substitution. And so we'll work on that next. And so what we're going to do for these two integrals is let u equal that inside function of cosine, which in both cases is 2 theta, which is pretty convenient. I'm just going to use one set of u substitution. I guess at this point you could technically skip this step if you know how the u substitution will affect each integral, but I'm just going to show it anyway to avoid any potential confusion. So we're going to let u equal 2 theta, which means that du d theta, the derivative of u with respect to theta, is equal to 2, which tells us that du is equal to 2 times d theta if we multiply both sides by d theta. Now that's going to work pretty nicely for this integral because du is equal to 2 times d theta, and we have 2 and d theta in the integral. But that's not going to work as nicely for this one because we just have d theta. We don't have 2 times d theta. So for this integral, we will also need to divide both sides by 2, and we'll have du divided by 2 is equal to d theta. So we can replace d theta with du divided by 2. Okay, so this integral, we're replacing d theta with du divided by 2, but this one, we're replacing 2 d theta with du. All right, I hope that makes sense. So if we simplify, this will be equal to 18 times the integral of 1. The integral of 1 is just going to be theta. So we'll have theta evaluated from pi divided by 2 to 2 pi divided by 3. And then we'll add that to 18 times the integral from this lower bound of theta to an upper bound of theta. But we're going to rewrite those to be in terms of u. I'll come back to that. And so before we do that, we'll have cosine of u times du divided by 2. All right, 2 times theta was replaced with u, and d theta was replaced with du divided by 2. Now for the bounds of integration, we need to change them from being in terms of theta to being in terms of u. So after integrating, we don't have to convert back into terms of theta. We can just continue to work in terms of u. So what we'll do is plug these values of theta into what we set u equal to find our new bounds of integration in terms of u. And so since u is equal to 2 times theta, we just have to multiply our angles by 2. And we'll have to do the same thing over here for this integral. So 2 pi divided by 3 times 2 will give you 4 pi divided by 3. And then pi divided by 2 times 2 is just pi. All right, then we'll add that to our next integral. The integral of 6 will be 6 times theta. So we'll have 6 theta evaluated from 2 pi divided by 3 to pi. And we will subtract the integral of 8 cosine theta. The integral of cosine is sine. So we'll have 8 times sine theta evaluated from 2 pi divided by 3 to pi. And then finally we have this integral, which we're going to rewrite in terms of u. So we'll have plus the integral between these two bounds of integration, but let's convert them to be bounds of u. So let's multiply them by 2. We'll have 2 pi for the upper bound because pi times 2 is 2 pi, and 2 pi divided by 3 times 2 will be 4 pi divided by 3. All right, and then we'll have cosine of u du. We replace 2 theta with u and 2 d theta with du. Okay, so now this integral and this integral are entirely in terms of u. We don't have to worry about working in terms of theta. We can just integrate and evaluate. And so let's move on to our next step. We can evaluate theta at 2 pi divided by 3 and then subtract the evaluation at pi divided by 2. So this is equal to 18 times 2 pi divided by 3 minus pi divided by 2. Then we'll have plus this integral. If we pull this 1/2 to the outside, 18 times 1/2 is 9, and then the integral of cosine is sine. So we'll be multiplying by sine u evaluated from pi to 4 pi divided by 3. Then we'll add that to 6 theta evaluated at pi and then subtract the evaluation at 2 pi divided by 3. So we'll have 6 pi minus 6 times 2 pi divided by 3. Then we'll subtract 8 times sine theta evaluated at pi minus the evaluation at 2 pi divided by 3. Sine of pi is 0, so we're actually going to have 0 minus 8 times sine of 2 pi divided by 3. All right, and then we'll add that to the integral of cosine u, which is sine u. So we'll have sine of u evaluated from 4 pi divided by 3 to 2 pi. Okay, now if we take it one step further, we'll distribute 18 through this quantity. 18 divided by 3 is 6, so we'll have 6 times 2 pi, which is 12 pi. So this is equal to 12 pi minus pi divided by 2 times 18. 18 divided by 2 is 9, so we'll have 9 pi. And then we'll add this to 9 times sine of 4 pi divided by 3 minus sine of pi. But sine of pi is 0, so we're just going to have sine of 4 pi divided by 3. And then we'll add this to 6 pi minus 6 times 2 pi divided by 3. 6 divided by 3 is 2, so we have 2 times 2 pi, which is 4 pi. So we have 6 pi minus 4 pi. And then we'll be subtracting negative 8 times sine of 2 pi divided by 3. Sine of 2 pi divided by 3 is the square root of 3 divided by 2. So we have negative 8 times the square root of 3 divided by 2. Then we'll add that to sine evaluated at 2 pi minus the evaluation at 4 pi divided by 3. But sine of 2 pi is 0, so we'll have 0 minus sine of 4 pi divided by 3. All right, now if we simplify further, 12 pi minus 9 pi is 3 pi. So this is equal to 3 pi plus 9 times sine of 4 pi divided by 3. Sine of 4 pi divided by 3 is the negative square root of 3 divided by 2. So we'll have the negative square root of 3 divided by 2 plus 6 pi minus 4 pi. That's 2 pi. So we'll have 2 pi. And then we have minus negative 8 times the square root of 3 divided by 2. Those two negatives will cancel out. So we'll have plus. And then 8 divided by 2 is 4. So we'll have 4 times the square root of 3. So we'll write 4 square roots of 3. And then we'll add that to 0 minus sine of 4 pi divided by 3. And sine of 4 pi divided by 3 is the negative square root of 3 divided by 2. So we have negative the negative square root of 3 divided by 2, right? Because we have 0 minus the negative square root of 3 divided by 2. But those two negatives will cancel out, and we'll work on that in the next step, because next what we'll have is 3 pi plus 2 pi. That's 5 pi. So I'm going to write 5 pi, and I'm just going to cross those out so that we know that we dealt with them. And then we have 9 times the negative square root of 3 divided by 2. I'm just going to write that like this. We'll have minus 9 square roots of 3 divided by 2 plus 4 square roots of 3. That's just this term right here. So now we used both of those terms. And then we have plus the square root of 3 divided by 2 because those two negatives will cancel out. So we'll have plus the square root of 3 divided by 2. Okay, we're almost there. We just have a couple more things to simplify. We can rewrite 4 square roots of 3 to be 8 square roots of 3 divided by 2. So this would be equal to 5 pi minus 9 square roots of 3 divided by 2 plus 8 square roots of 3 divided by 2 plus the square root of 3 divided by 2. And so these two terms could be added together to be 9 times the square root of 3 divided by 2, right? 8 square roots of 3 divided by 2 plus 1 square root of 3 divided by 2 would be 9 square roots of 3 divided by 2, which would cancel out with this negative 9 square roots of 3 divided by 2. So these terms all cancel out and just leave us with an area of 5 pi. And so all that work led us to this answer of the area that is common to these two polar equations. This area in here, I know it's pretty small right now, but that area is equal to 5 pi. Okay, and so hopefully that whole process made sense. Once you get to the integration part, it's really nothing new. The hardest part is really just setting up those definite integrals to represent the area. All right, and so with that, that's it for this example, which is the last example for this video. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.